So Bitcoin plus privacy will become Zcash. I don't know if everybody's familiar with Zcash. It's pretty much the very first blockchain that enabled this sort of privacy transactions on chain. Then we have Aleo. So that's sort of the positioning of Aleo in this ecosystem, is that we're trying to enable privacy, but also the flexibility of programmability on top of blockchain. So I'll talk a little bit more about the off-chain side in a bit, and that also enables this unlimited application runtime. So blockchain execution here means, running sort of like in the Ethereum virtual machines, you have to, whenever the code that you write in Solidity, they're going to be compiled into bytecodes, right? And each bytecode means different steps. So you have to run all that on every single node in the blockchain, because everybody needs to run their Ethereum virtual machine. And then once they execute all this Solidity code, they'll update their state on their node, and every single node in the blockchain will do that. But in Aleo, it's a little bit different. Not everybody needs to run the execution. They just need to validate. Pretty much three types of roles. On the very far left, is validators, and then in the middle is the provers, and then on the right is developers like us. So starting from the developers, we're the ones who are creating magic. We're the ones who are coding the smart contract that can run on top of Aleo. And the language that we use to write Aleo smart contract is called Leo. It's a functional programming language for zk circuits. So if you're not familiar what zk circuit means, it's basically a sort of a setup for certain inputs to be passed in, so that make sure this input can pass through all these gates, and then at last it creates it has this sort of a proof result. So once you go through that, and then you create this proof result, and this proof result can be validated by different parties to ensure that, okay, you're based on the input, the public input, and the proof that you provided, and using my validation program that I run using these two input, the public input and the proof that you provide, I can validate that, oh, you actually ran the program correctly. I can trust you, but I don't have to know the details of what was the private input was, but I can still trust you. So coming back, with Leo, you're writing the smart contracts, and once you finish writing the smart contract logics, then you'll be running your codes, and the execution environment happens at the provers, so it's in the middle. The actual term is called Snark VM, so Snark Virtual Machine, and it pretty much what it does is, let's say you want to do a function call, like you want to do like a Uniswap, like a swap function, right? Normally on Ethereum, what you do is you send that request to Ethereum network, and some of the nodes or some of the miners are going to pick up that request, and then they'll broadcast that request to the other nodes nearby. That's first, and the second will be they will sort that transaction request into the block and then try to run it, blah blah blah. So that happens there. But for Aleo, it's a little bit different. Instead of sending that transaction request to the miners, but instead it has two approaches. So first, you can either run that request locally on your own device, just your own device. And by running it, you have your own input locally, and you generate, you run the Snark VM execution environment on your local device locally. And then after you run it, you create that proof, and then that proof creation process also happens locally. And after all that's done, what you do is you pass the proof that is generated and the public inputs that you step into this Snark VM for the execution. You pass both of these to the validators on the very far left, and validators you can just think of as like the miners in blockchain. You can think of them as the miners in blockchain from the Ethereum standpoint, but what they're actually doing is just validating the proof that is generated from these local clients, right? So what does it mean? So if you kind of compare, is that instead of running that code logic in every single nodes in the network, instead in Aleo, what they do is you only need to run once, and then you're generating the proof with the inputs together, and you just pass it to a group of validators to validate. And validate usually take about O1 time. So what does O1 time means? It's just constant time, and it's super efficient. So that's why we're trying to say it's like more scalable. Numbers of execution doesn't scale prover services, but it's still off-chain. You only need to run once. And they will be downloading the Aleo program, or they already have it on their local device from the validators, because as you can see, we just uploaded our Aleo program to program registry, right? So they'll be downloading that to their local execution environment, activate the start VM, and then they will run this Aleo program. Specifically, the example that I was giving is the Uniswap swap functions. So they'll be running that, and after they have this proof generated, after they finish generating the proof, they'll upload that proof to on-chain. So this will be the on-chain part. So after the off-chain execution is done, which is the far left, and then they will send the proof over to validators again, and the validators will get the proof result and then the encrypted data, and then they'll just validate the correctness of your execution, if it passes, and if it works, then they will update the entire execution result on chain, and also return to the user whoever called that swap request for an update. Say, hey, your transaction succeeded, congrats. And then once all these nodes are agreed on one single data, one set of data that they agreed on, then they'll upload it to the chain. So that's how they work. But with verifiable oracles, it's a little bit different. So instead of having multiple nodes that is running to fetch the same data, and then have everyone to agreed on and then submit it on chain, with zero knowledge, you can just whoever fetched the data, just create a proof of your fetching, right? The fetching process, and then I'll just validate you. I'll just check like, oh, okay, you have a proof, you have your input. I'll check it. Okay, it works. So I'll trust you. As simple as that. It saves a lot of the overhaul. And private and compliant stablecoins will just be providing reliable financial transactions with privacy guaranteed by TradFi. So TradFi is still it's a pretty general term. I would even say just a marketing term too, but it's just trading in general. And for web developers, there are different solutions too, like zero knowledge gaming. So verifiable randomness. This is something very hard to achieve. When there's zero knowledge proof, technically speaking, random number generation on top of zero knowledge proof is just pretty hard, almost impossible. But we do provide a random number in Leo language, so which developers can utilize. And also there's privacy preserving machine learning. So something like for instance, like maybe like you develop like a privacy preserving machine learning model, and then the inputs. We should really cover this after the Leo language introduction, but because of the nature of Leo language, that you can set variables into privates, so that creates a possibility of privacy preserving machine learning. And zero knowledge authentication, pretty much like I can review that I'm over 18 without showing you my ID, something like that. Very expensive. And if you want to create like a proof on top of a very large number, then the proof generation gets extremely one level more complicated. So you want to be really careful of what kind of numbers that you're using, as small as possible, definitely, and just So that's sort of coming from the blockchain performance perspective. That's why there's this requirement of you have to specify your numbers, specify your variables into the very specific data type. Yeah, but you can do casting among these, so that's totally available. Yeah, so there are different data types, 16 primitives to be exact. So on the very left, you have fields, scalar, groups. So these are not very intuitive to us if you're coming from other programming languages. But you can kind of understand field as, so on zero knowledge, there is something, they usually work with a prime number field. So it doesn't really go above that prime number field. So whenever I want to create a proof, I have to work with numbers that is within this prime number field. So that's why there's this field element. So this field element is usually used for proof generations and also just some decryption and that kind of related operations. So you want to specify your input as field elements, and that the range of that field is set in stone with the Aleo blockchain. So Aleo, I forgot the exact number because it's really complicated looking. But yeah, you have to fit your number within that prime number field. If your number goes above that field number, the field size, then pretty much it will just take the modulo of that number of the entire prime number field. So just the remaining. And scalars and groups, they kind of work together. It's pretty much for ECDSA. How do I explain? So ECDSA is sort of like an encryption scheme where encryption and decryption scheme where you're having different pairs. Maybe I should have put a graph up here actually. Yeah, but it pretty much like if you want to do encryption and decryption, then you want to use groups and scalars. And scalars are the ones that is used to multiply, to divide with the group numbers. So you can think of scalar as the coefficient for group variables. But we'll see these three in actions in a bit. But later, and then we have binaries, which is Boolean, which in a lot of programming languages we already have, which is true and false. Data type, we also have address and string. Integers, we got a lot of unsigned, unsigned, and also just integers in general. And then we have structs and records. Records might be a little bit unfamiliar to most people, which I'll explain in a bit. Yeah, so if we look at the very left, the struct type is just how you want to define a sort of like a struct, like in any other languages. But record is a little bit different. So record is what we really use as to show the sort of like the asset transfer sort of relations on blockchain level. So let's say I own about 10 tokens. So how it shows up in blockchain, so on Ethereum, how it usually shows up is that it just shows that under this smart contract, this token, it will have an array that stores that, hey, under this address, under this user address, there's this amount of balance. So it's just like a state model. And for every sort of transaction, let's say I purchase like 10 more tokens, then all they need to do is just changing that array of, let's say it's a key value pair, and they would just use my address as the key, and then the value would just add 10, increase 10 there. And all they need to update on Ethereum client, it will be just update that state. But on Aleo is a little bit different, because Aleo is not a state model, it's a UTXO model. It's pretty much the Bitcoin model. So everything is sort of a transaction histories, right? So let's say if I want to own like 10 token records, then I need to create those token records, and then I need to transfer that into my address, and I will be only owning these records. And if I want to transfer, like let's say I minted 100 tokens, then I'll be creating 100 tokens and then transfer that records to me. So I'm owning the records instead of the tokens, although it's like token records. And then if I want to transfer 10 tokens to some other folks, then what I will do is just split this one record into two records of 90 tokens and 10 tokens. And this 10 token records will send over to someone else that I wanted to give to, and 90 token records will stay within me. So it's not like just changing a variable in a map or array that kind of a simple, but instead is you have to manipulate with the records, and on blockchain too. The entire sort of transaction history is actually shown as changing in records. So if you look at this very top, you have mapping. So mapping is pretty much mapping in another language is you have key and value. Yeah, so mapping is pretty much just key and value pair, right? This is how you this is how you declare mapping. So what this means is, I'm creating a mapping for a variable called balances, and the key of this balances mapping is address. The value is unsigned 64. And I'm also declaring a token standard records, which it will specify the owner of the token and the amount of tokens. And struck here will be the message. It would include the sender's address and the objects in unsigned 64. So this is the sort of the very specific part of Aleo that gets kind of tricky to understand. So there's transition functions, there's finalize functions, and there's function functions. So all three of these are functions, but they're named differently. How are they different? So for everything that is written inside transition functions, it happens off-chain. So let's say if I want to do a Uniswap, actually it's a bad example. Let's say if I just want to decrypt something. If I wanted to decrypt something, then it doesn't have to run on-chain. Then I can just write the decrypt function inside this transition function, and then I can just fetch that result locally. I don't even need to submit the final result to the state or anything, because it's just I need to decrypt something for my off-chain executions. But after transition function is done, then you can see it's followed by this part. It's called then finalize. So what does this mean? And you can see the name is also same too. Like the transition function and the finalize function, they're named the same, but it's just the prefix, the transition and finalize is different. So the difference here is, if I call this mint public function, what's going to happen in this smart contract is that it's going to first execute the transition function off-chain, and then once the code inside this transition function is done running, then it's going to pass the proof and the input to this finalize function. And this finalize function runs only on-chain. So finalize keywords is trying to specify whether this function is specifying the function is running on-chain. So transition is to specify a function that runs off-chain. So now that I'm passing the proof and the inputs to the finalize function, then this part will actually run by every single validators on the network. And the result will also be updated to the mapping, because this is what they're doing, right? Setting the mapping with the account and receiver, and also the amounts. Yeah. And so what about this function? What does this do? So pretty much you can just think of it as like a helper function, or in a easier term, sort of like just make the code prettier. So instead of having this code, A plus B, written inside one of these, they want to separate the logic out so that it's more modular, the code is more reusable. You can just write it inside the finalize or transition if you want, but you can also just write it outside. So that's totally up to you, up to your coding convention. Yeah, so that's sort of the general outline of how Leo smart contract works. Forward to understand for a lot of the developers actually, because it's just specifying whether I want to run something off-chain or whether I want to run something on-chain. But like you mentioned, there might be something that is more zero-knowledge focused, and it's just really hard to get your idea. get your heads around. I think there's some examples. It's like these libraries. Yeah, so something like this. So these are hashing libraries that you can use. So this will be really just it depends on the application that you're building, and you can choose any kinds of hash that you want, and also you can convert your hash into different variable types like scalar, groups, or field. And these are some of the things that are supported, but not a lot of people know how to use it. But pretty much it's just like SHA-256, which you can see here, and there's like a couple other options, but there are some of the ones that are, Poseidon 248. These are some of the hash functions that are not supported in other chains but supported here. So it's just worth taking a look. And also this commit, even myself, I haven't really used it yet, but yeah, this is like a commit function. I am not 100% sure what this is for actually. Yeah. So here's something like this too. But other than that, everything else is very similar when it comes to just programming Leo smart contracts, because they really made it a way that is just very similar to your original coding experience. Besides, you need to think in another dimension where you want to run something on chain or off chain. So you want to be more careful, be more mindful of that. But other than that, everything else should be a very similar experience, except commit. I'm not too sure of that myself.
What makes Poseidon different from other hash functions?
So hash functions is another sort of a topic, but Poseidon is just faster. Yeah, it's faster than SHA-256. It's a pretty new one. There's even Poseidon 2, which is even faster, and there's like Blade 3, just all these sort of namings. But yeah, eventually it's just improving in performance. Yeah.
I guess one of the other points I was kind of bringing up with like zk proofs, would we need to know like the way that the Aleo virtual machine works, or bytecode, or that sort of thing?
So if you can, like, if you want to, so how this works is, if I create a new Aleo smart contract sort of project, then this is how the entire sort of project outline folder looks like. And if we build it, it's going to create a file called main.aleo under build folder. So what is main.aleo? So Aleo is pretty much the bytecode level language that you can use to write your own circuits. What's different from Aleo to Leo is pretty much you can think of Aleo as the assembly version of Leo language. So Leo will be the front end language, and then Aleo will be the back end, or just like compiled version. So yeah, if you want to really optimize your code and make your ZK circuit more, I don't know, just smaller, I guess, more optimized, you can do so at the Aleo code level. But still, even that, you don't need to touch the virtual machine. Yeah. So the virtual machine should be just an instance that you run without you do any sort of configuration. Yeah. But if you want to optimize your code for ZK circuits, you can do so at the Aleo code level. So just like in Solidity, just like in Ethereum, instead of writing Solidity, you're writing EVM bytecodes for your program. So that's more hardcore. There are frameworks for that, something like Huff. Pretty much just having you to, it's a framework for you to write EVM bytecodes smart contracts. It's kind of complicated, but it gets the job done really well, and it's more efficient to write your smart contract that way. But yeah, but for Aleo, it's a little bit different because a lot of the computation can happen off-chain. So the computation resources might be, for the off-chain computation part, you don't have to consider too much about the optimization but of course you would want to just for the better performance. But since off-chain computation you only need to run once, so you don't have to be that mindful compared to the on-chain computation part. Yeah. So if you want to optimize, I would definitely recommend optimize the on-chain computation parts by codes, Aleo codes. Yeah. Leo wallet that we just downloaded here. So that will be a wallet extension on the website, like a Chrome extension. You can use this for sure. But you can also since we're just testing and playing around, we can also use this terminal command called Leo account new. And if I just type enter, then it will create a new Leo account for me. And what it contains is private key, view key, and address. So what is private key? Private key is basically like the sort of like the most important information of your wallet. If you expose your private key to other folks, they can use that private key to retrieve your wallet and gain access to your wallet for everything. They can just do anything with the private key. So you don't want to expose private key like I'm doing right now, actual message of that transaction instead of viewing the encrypted message. So yeah, view key is pretty much just a decryption key to see transaction activities. So yeah, once your account is created, you can gain your test tokens by going to Aleo faucet. So it's this. What you want to do is text this phone number with this message. Send 50 credits to this address. And this Aleo1XXXX is pretty much the address here. So you want to send a text message to this, and then you will receive your 50 credits in no time. It's not the best experience. I hope they use another approach, but this is what Aleo has. So yeah, stick with it, guys. Where was I? Yep. But since it's like local testing, so I don't think you need to have testnet tokens unless you want to deploy it to call this main function, because by calling this main function is still a transaction request, right? And this transaction request will be stored. This history will be stored on blockchain. But some parts of this request will be public, some parts of it will be private. So the public part will be the input A, but the B will be private. So that technically that's sort of what it means. And the result C it will also be private. So the output from this transaction will also stay private. So yeah, from other users who are not the one who call this main transaction request, all they can see is just I injected a number into this function, to this A variables, and I know that there are some other variables or whatever things that happen for B, and there's something coming out as C, but I don't know what the values are. So that's how it's stored. That's how it exists in the blockchain here. If you call this function. So what this code does is just taking the public A input, private B input, and then getting the C private output, and then return it, right? And under this input file, so what this does is specifying if I wanted to test out some of these functions, this main function, then what are some of the inputs that I want to put it into? So these are just some of like test scripts or demo scripts, and you're just writing some toy data to test out some of the features. So you have public A, which is 1, and then private B, which is 2, right here. So the result should be 3, right? So let's try to run this. Leo run main. So by specifying Leo run main, I'm telling the Leo command line that, hey, call this main function, not the main.leo, but call this main function. And if you want to find the input of this main function, it's either I specify it here, you know, I specify here, and then if I didn't specify, then go to this input folders and look for a .in file, and inside there I should have specified it, so which I have, and it will take the inputs from here 1 and 2, and the result is 3. So yeah, that's how the folder structure and how the testing with all these code works. Out of my 100 token balance, which will get the sender's balance, and from sender's balance, I'm going to create a new record, which is the 90 tokens that is remaining, and also I'm also creating a token record for the recipient, which will be the 10 tokens, specifying the owner is the receiver, and I'll return both of these records after calling these functions. So this is exactly what I'd explained at the very beginning. Say I own 100 tokens in one record, and if I want to split this 100 tokens, if I want to transfer part of this 100 tokens to someone else, then I need to first split this 100 tokens into two records, and one of the records will be the amount the amount of tokens that I want to transfer to, let's say, Clifford. Then I'll send this record to him, and I'll keep the second half of the record to me myself, and to prove that I actually own these tokens. Yeah, so this is what it does. It's not that complicated, but I'm kind of over explaining to everyone just to make sure everybody understands it. So now let's go into inputs. So now that we have defined, mint and transfer functions, I've also written some of the inputs that you can follow. So you can just kind of copy from this GitHub, define input section, and then just copy this and then paste it. Specified its owner and specified its balance. Now I want to do a transfer. So this transfer will be, it's going to take the receiver's address and the amount of token that they're going to be getting, and the input of my token record. So this token record will not work because it's actually not the record that I own. It has to be the record that I own, which is this, the one that I just minted. So I have to copy this, and then I'll paste it on here.
Input token.
And just get rid of these. So now that I have what I have specified is, okay, I'm going to send 10 tokens to this address of the token of this token that I own, that is created from the mint function. So I'll just call Leo run transfer, which is this function name. And as you can see, it has created 10 tokens for this address that we're sending to, this 1yn6h.